Today we're going to start looking at Chapter 5. We're essentially going to focus on two sections from Chapter 5, Section 5.1 and 5.3, looking at the transportation model and the transportation algorithm to solve transportation models. First off, what is a transportation problem? It's a problem that looks something like this. So a company has 3 warehouses and 4 distributors. Because of the locations, it costs different amounts to ship from each warehouse to each distributor. So we have something like what you see here. The numbers in the table is the cost for shipping 1 unit from each warehouse to each distributor. So for instance, shipping something from warehouse 2 distributor 3 costs $32. Each warehouse has a certain number of items in stock, and each distributor has certain requirements. And the question is, what is the cheapest way to move the materials from the warehouses to the distributors to satisfy their requirements? That is a classic transportation problem. If you were to write it down in terms of what we've seen so far for linear programs, you would get something like this. You would be minimizing the cost, and here's the cost, the equation for the cost, subject to these items are the items that are shipped from the warehouse. So it says warehouse 1 has 10 items, 10 units of an item in it. So this says the amount that it ships to distributor 1 plus the amount to distributor 2 plus the distributor 3 plus the amount to distributor 4 can be no more than 10 units because it doesn't have any more than that. So the first 3 equations talk about the supplier side. The next 4 are the distributors. So the distributors have a certain requirement. So for instance, distributor 1 says the amount of stuff that they get from warehouse 1 plus the amount they get from warehouse 2 plus the amount from warehouse 3 has to be at least equal to 20. They have to have at least 20 because 20 was their requirement. And of course, everything has to be positive. So your variables here are xij, such as x22 is the amount of item that is sent from warehouse 2 to distributor 2. So xij is the amount of product from supplier I to distributor j. But we can write things a little bit more compactly, again, using that table that we started with, where the numbers in the table is the cost of shipping from each warehouse to each distributor. On the right-hand side, we have the amount available in each warehouse. And on the bottom, we have the amount that each distributor requires. So this is a much more compact way of writing it rather than writing out the whole equations. And what we're going to see is that when you have a transportation problem, with the characteristics like what we've just seen, there is a more efficient way to solve it than writing out the whole equation and solving it that way. There's another method to solving these. First thing to note here. Note that this is what we call a balanced problem. You add up everything on the right-hand side, you have 100 units. You add up everything on the bottom, we have 100 units. The supply exactly equals the demand. That's called a balanced problem. And we're going to see that if you have an unbalanced problem, that there's a couple of methods to use to turn it into a balanced problem. This method for solving transportation problems requires a balanced problem. So first off, let's just take another peek back at our linear program. The linear program formulation, because we're balanced, it means that everything is going from the warehouses to the distributors. In order to meet the requirements, everything has to be shipped. Because everything has to be shipped, that means we don't have inequalities. We actually have equalities in our problem formulation. So we have that things are equal because everything is being shipped out of the warehouses and the demand is being met exactly by the distributors. But now let's take a closer look at these constraints. What is happening here? Take all of the supply constraints, the things from the warehouses, and add them all up. What do you get? You get every Xij is in there once. So everything on the left-hand side, when you add them all up, you get the sum of all the Xij's. The right-hand side gives us 100. So the sum of all the Xij's equals 100. That's what you get from adding together all of the supply constraints. What happens when you add together all the demand constraints? You get that the sum of the Xij's over all the Xij's is equal to 100. When you add your supply constraints, you get exactly what you get when you add your demand constraints. What does that mean? This means that one of these things in here is redundant. In other words, you can take any of those equations, any one of those equations, drop it out of the constraints, and it won't make a difference. Because in this problem, if we take the three constraints, the three supply constraints, add them together, and subtract the first three demand constraints, what you are going to get is the last demand constraint. That's an extra one. It isn't adding any more information to the problem. What that means is that even though we start with 7 constraints, in reality there's only 6 of them that are important. And you can essentially drop any of them, and you're going to get the same exact problem. There's extra information in there. Now, that is important when you start to look at why the transportation algorithms work. But we start out with, if we have I supply centers and J demand centers, we start out with I plus J constraints, but in reality, we have one less. We have I plus J minus 1 constraints because one of them is extra. What does that mean? Well, that means that in this case, instead of 7, we essentially have 6 constraints. Remember when we build our linear programs and we build our tableau, what do we get? We get one, we add in one unique variable in each. That's your basic variables. What that means is that for this problem, we can do it with m plus n minus 1 basic variables. Because one of those equations is extra, it means that we have m plus n minus 1 basic variables in our linear program. So any basic feasible point has that many basic variables. So now we're going to look at how to solve this, keeping in mind that that's the number of basic variables in our linear program. So what we're going to do is I'm going to give you a process that solves these problems, and then we're going to go back and take a look at kind of why this works. And the number of basic variables is important. You're going to see this cropping up. So we're going to look at something called the minimum entry method. Go to the cost matrix, so that middle matrix of all the items and the costs that it costs to ship. Find the smallest one, ship as much as you can along that line. We're going to adjust the supplies and demand to account for that. We're going to cross out a row or column no longer in use. Either a warehouse has been emptied or a supplier's demand has been totally, or a distributor's demand has been totally met. And then we're going to keep repeating that procedure. And we're going to continue this until there's only one row or column left. And that will be totally determined by what we've done so far. What we do in this is when we do this process, we are going to end up circling exactly the right number of cells. Remember, each cell in there represents a variable in our linear program. Those are our basic variables. Okay, so now we're going to solve the problem and see this technique, this initial technique. What we're going to do is, first off, you find the smallest number in here. This is the smallest shipment cost. So you circle that, 16. Now this is going from warehouse 3 to distributor 2. You look at the amounts. Well, warehouse 3 has 50 units. Distributor 3 requires 30. So what's the most you can send along there? Is 30. So we are going to send 30 units along that supply chain. That means his demand has been met. That's 0. And this warehouse now has 20 units. And what I'm going to do now is I'm going to cross out one of these numbers or one of these lines that is all done. So distributor 3 is all done. I cross that out. And now I look at what's left on the matrix. I do the same thing. My next lowest one is 19. What can I ship there? Well, I have the distributor requires 30. There are 40 in the supply. So I'm going to ship 30 units along there. That means that distributor has met all the requirements. That warehouse now has 10 units left. And again, I cross out either a row or a column that has 0 requirements on it now. Continue with this. Now look at what I'm left with. What's the smallest number that I'm left with? It's the 22 here. Now, on this one, we have that warehouse has 20 units. That distributor requires 20. So that gives us 20. That means the distributor requires 0. This warehouse requires 0. And now I have to cross out either a row or column, not both, just one of them. And you can actually choose whichever one you want. So in this case, I am actually going to cross out the row. Okay, but you only cross out one. Now we continue looking at the next one. I have 22 here. I can only ship 10 along there. That means that brings that number down to 10. That number goes to 0. So the next one I cross out is that row with all zeros. What's left? 2 items. So I'm going to circle the next lowest one, the 26. But notice here, this distributor, the line hasn't been crossed out, but it does actually have a 0 on there. That means I have to choose 0 on there. And then I have to cross out the column because that's the 0 column. The other one still had 10. What's left? I have 1 number left. And I can ship 10 units along there. And that's the last of my requirements. I have now found a way of shipping 100 units from my warehouses to the suppliers. Now the catch is that this is probably a fairly good idea, but it probably isn't optimal. So now I need to figure out what to do to make it optimal, that there's probably a better solution hiding in there someplace. But first I want to point out something. We had 7 constraints to start with. I said one of the constraints was extra. What have I done? I've circled 6 numbers. What have I circled? I have circled the numbers representing x11, x21, x22, x33, x24, and x34. Those are going to be my basis elements in my linear program. That's not important right now for the algorithm. I just want to point out that when I do this, I end up circling 6 items. Those form a basis in my linear program. So here's what we figured out. Now we have a feasible point, but it's probably not optimal. In a linear program, when this happens, you have to pivot. So how do we pivot in this? We use something that's called stepping stone method. And this tells us how to pivot. Remember what a pivot is. A pivot when you're doing a linear program is taking an element from your basis, moving it into a non-basis, becoming a non-basis variable, and taking a non-basic variable and moving it the other way, moving it into your basis. That's a pivot. And really what you're doing is you're rewriting your linear, your constraints, and your objective function in a way that is improving your solution. So what we're going to do is we're going to do the same thing. We're going to choose a non-basic variable to enter the basis. We're going to find a cycle with this variable and the previous basis variables, and that's going to determine whether or not entering this variable provides a better solution. So how do we do that? Well, first off, let's just take an example. If I pick this number down here, the green highlighted things are the things that are in my current basis. Let's say that I pick this variable, which is x31, and I say, okay, this is a non-basic variable. I want to put this into my basis. Now something has to come out of my basis. And how do I do this? Well, if I am to throw some elements on there, that means that I'm now going to ship some things from warehouse 3 to distributor 1 instead. But everything is already taken account. So I need to figure out how to adjust my supply, my shipments, so that I'm still meeting all of the demand. So what happens? So let's say that I ship S units along that line. You know, S can be any number. What happens? Well, what I'm going to do is I'm going to look for a cycle in here using that point and using only my basis elements. And this cycle will always exist. So what do I mean by that? In this case, if I go up to here, go across to here, and go across to here, and back again, I've found a cycle. So I've found a number of points where going up and crossways, I only land on my basic variables. Now with this, I can start to say, well, how can I adjust my shipments so that it is still a valid solution? Remember, I started by saying that I'm going to ship S units along here. Well, if I ship S units to distributor 1, that means that he's now getting an extra S units, so I have to drop the number of elements here. Well, I dropped that. Now warehouse 2 doesn't have as many, so it has to increase here. So I go to the next point of my cycle and it has to decrease here. And by doing this, I guarantee that all of my supply and all of my demand is still going to be met by alternately increase by S, decrease by S, increase by S, decrease by S as I go around my cycle. And you can see that's what I've done here on the bottom. My first one, I've gone up by S. This is my new one. To compensate, I have to drop something in here by S. So distributor 1 ships S less units, or gets S less units from warehouse 2. Well, now warehouse 2 is shipping less units, so they have to ship some extras. They ship them to distributor 4. Now distributor 4 is getting too many, so they have to ship S fewer units to, they have to receive S fewer units from warehouse 3. And now the cycle brings me back to where I started, and you can see that everything adds up again. What I've done is I've found another way to ship things. But now, remember what I'm trying to do here. I'm trying to take this variable, the variable x31, and put it in the basis. That means something has to come out. So take a look at the adjustments that I've just made. What's the biggest adjustment possible? Well, I can never ship less units than 0. So how can I do this to bring one of those shipments down to 0? Because this is 10 minus S, it's saying that I'm going to ship 10 minus S units. That means S can be no more than 10. 10 is the most I can ship, or the biggest change I can make. This one is 20 minus S, so that means 20 is the biggest I could change it for that. Well, the 10 overrides it, so this means I can only put at most 10 units through from warehouse 3 to distributor 1. But what happens when I do that? That becomes a 10. That one becomes a 10. That one becomes a 0. Now I've found something where I'm shipping 0 units. That's the variable that is going to leave. So in this case, x31 enters the basis, and x21 leaves the basis. But now what happens to the overall cost? So this is still looking before I've left the basis. What's happening here when I'm still using kind of the variable S? Well, I'm shipping extra things through there. So every extra unit through there costs me 25. This one, I'm shipping less. So I'm saving things by not shipping through there. I save $22 for every unit. The next one, I'm shipping more. It cost me $26. The last one, I'm shipping less. I save $31 for everything, every unit. You add all those things up, which means that every unit that I ship through 3 from warehouse 1 to distributor 1, from warehouse 3 to distributor 1, I am saving myself $2. So it makes sense to put as much as possible through that pipeline to then adjust to a new solution. Because every time I do, I save money. So using what I just talked about, I'm shipping extra as much as I can through there. That now gives me that variable with 10 units through it. That variable or that shipping line, I've taken everything out of there. So that drops out of the basis. I now have a new basis. That is how you do a pivot on a transportation problem table on the Tableau. Now we have a new basis with a lower cost. Now, one of the things to keep in mind here is that last time I just picked one of the units and did some calculations, showed that I could put some things through there. I can adjust my table to still satisfy everybody's demand. And I found a cheaper way of doing it by doing that. One important thing to note is that no matter what element you choose from here, every non-basic element, you are going to be able to make a cycle like we just talked about. So for example, if I were to pick let's say I pick this element to put that I'm gonna investigate moving things through from warehouse 1 to warehouse 2. Can I build a cycle through that? Well, here's my cycle. I start here. I go over here to this point. Well, now I start going down. I go over to here. I go up to here. I go back to here and up to there. So you see, I've built a cycle through here that is allowing me to adjust. So I would add items to my new variable. I would take it away from the next one. I would add to the next one and so forth all the way around the cycle. Now the question is, how do I find a basis element or a non-basic element to enter the basis that's going to give me a cheaper route? So taking that previous example, if I were to introduce x12 in the basis, the one that I just talked about, what happens? Well, my cycle, as we saw, went like this. So what happens? I'm introducing that new one. I put s in there. This becomes 10 minus s. The one on the bottom left becomes 10 plus s. On the bottom right becomes 10 minus s. The next one up becomes 10 plus s. And the final one becomes 30 minus s. What's the most that I can adjust this? Well, as I go around the cycle, I have a 10 minus s, a 10 minus s, and a 30 minus s. So my s has to be less than or equal to 10. And in fact, you would try to make it as big as possible if it improves things. But now, what happens? I'm going to take these lines out so I can see my numbers again. So what happens as I go around here? Well, as I go around here, my change in costs is equal to everything starting from my 2, 1, or my 1, 2 variable, it adds 36s. My next one to the left saves me 22 for everything that I don't put through there. My next one adds 25s. My third one saves me 22s. My fourth one adds 26s. And my final one saves me 19s. What does this all give me? I kind of do them in pairs. I get 14s plus 3s plus 7s, which is 24s, which means if I make this change, it is going to cost me extra. So this is not a good change to make. So what we found, so in the previous example, we saw a variable that enters the basis that saves us money. In this case, if I choose this new variable, I lose money. So how do I find which variables to enter the basis? When we're doing a linear program, we have these rules that say that you take the most negative number on the top row, you choose the ratio that is the smallest, and that's what enters the basis. Well, so how do we choose our new variable here? And this is something called the UV method. So you assign to each row and each column a number in a certain method, where the UVs, the UI plus the VJ equals Cij for every basic entry. And then for all the non-basic entries, you're going to compute this thing. And you find your Cij that is the most negative. If they're all positive, then you've reached your optimum value. So let's see this in action. So here's our tableau. How are we going to figure out these UV values? Well, it says that you start with the first row, which are the U values, equal to 0. So we're going to set U1 equal to 0. That's my first row. Then I look at all of the basic entries on there, and I find the values so that the U and V add up to the number, the cost for that line. So if I set V1 equal to 22, that works for that basis element. Now I can look down that row. I have a 31. This gives me U1 equal to 9. I look along this row where I have the U1 equal to 9. I have a couple of other entries in here. That gives me V2 equal to 10. And the next one gives me V4 equal to 17. I look down there. I can now get that was U2. I can get U3 equal to 5. And I can get V3 equal to 11. That gives me my UV values. What does this mean? These are now going to give me a way of figuring out what can and can't enter my basis. So now this tableau on top As you can see, the numbers are calculated on there. Now to see what variables might enter my basis, I started looking at my non-basic variables. So for instance, I look at my 25. What do I get? Well, I get for here that C31, that shouldn't be 27, that should be 25. The cost for that through that line minus the U value and the V value for that row and column. So minus 22 plus 5. That gives me a minus 2. What does that mean? That means that I can pivot through there and I'm going to improve things. So after I pivot, which we've already done the pivot in a minute ago, that's what I get. I recalculate my UVs, start with my U1 equal to 0, add up or get my values for the UVs for every row and column, start looking at every element in here. So I look at all the non-basic elements and doing the same thing. So for instance, my C12 is my C12 star. That's equal to 36. This is my C12 here. It's equal to 36 minus the sum of the U and V for that column, 12 minus 0, which is equal to 24. My C13 star, that's my next one in there, is 24 minus 13 plus 0. So 24 minus 13, that's 11. It's positive again. You can go through all of these, all of the non-basic variables, and you'll see that every one of them is positive. When that happens, you have an optimal tableau. So now we've figured out how to ship those items for the cheapest possible cost. And it's shipping 10 items from warehouse 1 to distributor 1, shipping 10 items from warehouse 3 to distributor 1, and so on through all of your basic variables. Okay, so that is the algorithm for transportation problems. We do have a case where you can have degeneracy. Now remember, we had degeneracy in our normal ones, in our normal linear programs. It can happen as well in these methods. So note here, I've calculated my U and V values. One thing to note is that I do have a negative U value, so my U and V's can be negative. Okay, they don't all have to be positive. But then if I figure out my C's, what do I get? Well, I'm just going to jump right to C31 star. And what do I get for this? My C31 star is equal to 10 minus 7 plus 4, which is minus 1. So it tells me that I can improve my solution by introducing that variable into the basis. So what happens if I do that? Well, I have a pretty simple cycle, so you can see what the cycle is. From there to there to there to there and back again. So I introduce S in here, that becomes 10 minus S, that becomes 10 plus S, this becomes 0 minus S. Oh, my S can be no more than 0. So what does that mean? That means that I am going to introduce this variable into the basis. I am going to take this one out of the basis, but I can't change any of my numbers. So the amount of stuff the direction that I'm shipping things stays the same. My shipping plan. My UV method has told me to introduce a new thing into the basis, but when I actually do the pivot, I don't actually improve. So this is the same as when you have a linear program, having your objective function being parallel to one of your lines if you're thinking in 2 dimension, to one of your constraint lines. So you're jumping from one corner to another, but you aren't actually improving your solution. The same thing can happen in these types of problems. Degeneracy happens when you have a zero amount of goods going from one place to the other. Okay, so now we're going to take a look at some of the theory of what's happening here. And here's an example problem, and we're going to use this example problem for some of the theory. So we've got 3 warehouses, 3 distributors, and the numbers shown on here for shipping things around, or the costs. So, theory. Why does the minimum entry method give us m plus n minus 1 points? Well, that's the first item of the theory. We had this minimum entry method for bringing things in. Why does this always work to give us exactly the number of basis elements we need? And you can think of it in terms of, well, the rule says that every time you choose a variable to enter your basis, you strike out one row or one column. What does that mean? That's the equivalent of saying that I'm taking care of one of my constraints. And at the end, when you enter the last thing, everything's going to be 0. You will have a choice to strike out either the row or the column that it's in. On the last time you circle something, you strike out 1, and you're going to be left with 1 row or column that is not struck out. So you're going to end up with exactly the number of variables you need. Second thing is, how do we know this is a basic feasible point? So recall that a basic point is characterized by the basic variables uniquely being determined by setting all non-basic variables equal to 0. Okay? That's just from our general linear program. So let's assume that all of the xij not chosen are 0. When you do that, you can show that the ones chosen have to be exactly what you've determined by this entry method. So in other words, your non-basic variables through this entry method are exactly 0. Everything else is uniquely defined. And how do you show that? Well, you can assume that your m is less than or equal to n. So in other words, you have fewer rows than columns, or no more rows than columns. And by showing that there's at least one column with exactly one selected entry, that it's uniquely determined, and you just continue over and over again until you've chosen them all, and that will show that you are uniquely identifying a solution based on setting everything else equal to 0. So here's just stepping through. Here's some of the ideas of what we just saw. When I start with this problem, it says first thing I'm supposed to circle my lowest number. So I circle it 2. What am I really doing here? Well, that is my variable 1, 2, x1, 2. That variable appears twice in my constraints. So this list is my constraints. These were my supplier constraints, and these were my demand constraints. Every variable appears exactly twice. What my rule says, now I'm going to strike out either a row or column, something that's totally satisfied. Well, in this one, I ship 10 items through there. That means I strike out the row. What's that row? Well, that row corresponds to a constraint. So that means that I've essentially taken care of this constraint, that I've found a value for x1, 2 that totally satisfies that constraint. Everything else in that constraint has to be 0. And this is what happens over and over again. So why didn't I choose the other one? Well, that's not the one that's being totally filled. Or if they are both being totally filled, you just pick one at random. So you only choose one of your constraints that corresponds to the row or column that you just struck out. Then I do my next one. I choose the 3. This time I strike out the column. Well, my first one took care of that constraint. My second one is now taking care of this constraint. So that constraint is totally satisfied. And I just keep doing that. And as you go through them all, you'll see that you end up with choosing 5 of the 6 constraints. And that last constraint becomes my redundant one. Because remember I said that there is always a redundant constraint. That's my redundant constraint. So by going through this process, what I've done is I've identified 5 variables, and note that every one of those variables can now be a basic variable in this way. Here's what I get from writing it, from with the ones that are circled. I've said that I have one where there's nothing circled. That's my redundant one, so I'm going to drop that one out. Now I can rewrite everything in terms of those 5 variables. It's just through basic substitution, I can get x12 equals something, x23 equals something, x21 equals something, and so on, where these variables on the right-hand side are gone from the left-hand side. So everything on the left-hand side are my non-basic variables. The things on the right-hand side are my basic variables. So you can see how this is working out the same way that a linear program works with the simplex method. So, theory, a little bit more theory. Why does this UV method work? Okay, so what we saw just a minute ago was kind of what happens in the pivot. Why is the pivot working? And how is it similar to the linear programming pivot? That's what we just saw. Now we're going to look at why is this UV method working? And really what we're going to look at is, or what we're going to see, is when you use this UV method, really you are using the dual of your linear program. So think about the dual of our problem. What do we have? Well, our problem was we are trying to minimize a cost. And what's that cost? It's the sum of all the Cij's times Xij's, subject to a whole bunch of constraints. When you take that and look at the dual of it, and go back and look at the original problem to see exactly how this is working, what do we have? We have the dual is going to be maximize this sum. And what is this sum? These numbers come from our supplier constraints. These numbers come from our distributor constraints, or our receiver constraints. Subject to. Now this is going to say that ui plus vj is less than or equal to cj. What is this? Well, if you take a look at your problem and you start looking down at all of the variables in the constraints, you are going to get things like, sorry, I just noticed that this should be bj, vj. You are going to get every variable appearing twice. So when you are looking at the constraints, you are going to get constraints that look exactly like this. And you are going to get that your ui and vi are unrestricted. Because we started with equalities for our constraints, we're going to end up with unrestricted variables. Now I deliberately put this down as ui's and vi's because these are exactly the ui's and vi's that you calculate when you use the UV method. Okay? So to take a closer look at this, go back, look at one of the problems that we have, write out its dual, and see how it fits in this form, how it is going to look exactly like this. When we calculate those ui's and vi's, what are we getting? We are getting values for our dual variables. We are getting constraints that satisfy our dual, or we're getting values for those dual variables that satisfy our dual constraints. So really, when you are using the UV method, what you are doing is you are taking a basic feasible point for your original problem, and you are using it to calculate a solution for your dual, or a feasible point for your dual. This is using both the primal and the dual together to give you an efficient method of solving a linear program. Now, those points may not be feasible. How do we know when are they feasible? They are feasible when the UV method stops. What we are getting is we are getting a solution for our UV variables that is giving us the same cost. But those variables may not be feasible. When are they feasible? They're feasible when all of those Cij stars are positive. When that happens, we have a feasible point. When you have a Cij star that is negative, that means you are violating a constraint in your dual. So it's not a feasible point. When they are all positive or zero, that means that you have found a solution to your dual that is giving you the same solution for your objective function as you are getting for your primal. So you have a point for your dual, and you have a point for your primal that is giving you the same value for your optimal function for the two objective functions. If that, we know that the primal point is feasible, but we don't know if the dual point is feasible. When all of thoseCijs are positive, then we have a point for our dual that is feasible. And one of our theories says that if we have a point for our dual and a point for our primal, both of which are feasible, and both of which give the same solution for our objective functions, we have our optimal point. This method is using that to say, okay, we now have a feasible point with the same things. That means it has to be optimal. Okay. All right. So that was a little bit heavy in the theory. Now we're going to look at what happens when we have an unbalanced problem. So take a look at this. What happens is we have 60 units here. We only have 45 units here. So that means that we have more supply than demand. How are we going to satisfy this? What we're going to do is we're going to adjust this problem to make it balanced. And we're going to do this. We're going to add an extra column in here that takes care of it. We are going to add it in and say, well, we had 15 more supply than demand. So we're going to create this artificial demand for 15 units. And that is going to turn it into a balanced problem. So notice that we are now balanced. We now have a demand for 60, or we have a supply of 60, and we now have a demand of 60. So that, and we put the cost to 0, and then you can solve it from there, and you are going to come out with a solution. So you add this phantom distributor to balance your problem. You can also add in concepts like having a penalty in each warehouse. So let's say that we have an unbalanced problem with 60 units here and 45 units here, but you have to pay to keep the surplus units in a warehouse. So keeping something in warehouse 1 is going to cost you $8. Keeping something in warehouse 2 is going to cost you $6. Keeping something in warehouse 3 is going to cost $1. You can add in those penalties in that column. Previously, we set it all to 0, which meant that there was no penalty, but some things are going to have to stay in warehouses. This is incorporating the penalty. And then you solve it as you do a normal transportation problem. What about an inadmissible route? So in other words, what if we aren't allowed to ship things from warehouse 3 to distributor 1 for whatever reason? Well, when that happens, remember we had the big M method for solving systems of linear, or solving linear programs? We can use something analogous here and put a big M in here, which means that it's essentially infinite cost to ship something through there. So now you put it in there, and when you start adding up your numbers, or when you start picking your numbers, just remember your M is always bigger than anything else, way bigger than anything else in here. So it's always going to calculate that you're not going to put things through there unless you're totally stuck. Sometimes you will solve it, and it will say that you have to put things through one of these, and it means that you aren't going to get rid of your supply, you aren't going to meet your demand. Okay, but in general, when you now solve this problem, all of your shipments are going to go through things other than that line. What about if a warehouse must be emptied? So the warehouse 1 has to be emptied, but I've still got more supply than demand. So I want to make sure that everything comes out of warehouse 1 and then warehouse 2 with the other things. Well, here I've added my phantom column again, but I've added a cost of M for my warehouse 1. So the penalty of 1, a penalty of M. So it's an infinite penalty for keeping things in there. It is going to guarantee that that warehouse is emptied. All right, that was a fairly heavy one. This is looking at transportation problems and solving them. It is also an excellent example of how the primal and the dual work together to solve these problems. So I tried to give a bit of a flavor for how the transportation method matches back to our simplex method. Because really what we're doing is we're doing our simplex method, but in choosing our basis elements to leave and to enter, we are using the dual to figure that out. And we're also using the dual to figure out when we stop. So it's a really good idea to try some of these problems and try to understand that connection between the primal and the dual in a transportation problem.